Yeah, welcome everybody. Today I just wanted to present the current state of the tool that I've been working on the last couple of weeks, which is about the automated advisory generation. And let me share my screen. Can you see my screen or?
Yeah, we got it.
Perfect. So this is about the semi-automated advisory generation for dependency scanning. And if you have like any questions or something during the presentation, just ask them right away. Just interrupt me basically. So first, I would like to introduce myself. I'm Julian, and I have been involved in security. Basically, I did a master's related to security, which was about dynamic security testing and fuzzing related to web application security. I did a PhD in static analysis, which was mostly related to symbolic execution and constraint solving, but also in the context of web application security. And after that, I've worked for a company called Shift Left, where we were doing static analysis for, basically it was a language agnostic code representation, like a graph, and I was basically involved in compiler engineering for JavaScript and C#, and I also took care of the database that we had, where we stored the vulnerability patterns, which were like traversal patterns essentially. But today is about the GitLab advisory database, and at the moment, the curation, and I'm saying curation, I mean like addition or modification of advisories in the database is a manual process largely. And so we have like different data sources. At the moment, it's mostly NVD. The preparation of the advisories is basically a manual step, and then they're getting at a certain point 750 gymnasium. So this is like more or less the workflow. So first of all, there's the data feed that has to be checked, like NVD, for example, and we have to filter for relevant entries, and then assemble information from different sources, which is also not that trivial because sometimes NVD advisories may be incomplete or maybe even wrong. So this has to be cross-validated and cross-checked. And an example for that would be, for example, that in NVD there is no title field, so you have to obtain the title from someone else for an advisory that you would like to add to the GitLab advisory database. Then you, from that, you're creating a merge request, which is reviewed and then maybe edited, like there's a cycle, and at a certain point it's merged and then soon to the. So today's presentation is mostly about optimizing everything up to the point where things are getting merged into the GitLab advisory database. The tool I've been working on during the last couple of weeks, I just called it adbcurate, ADB for advisory database. You find the tool link on the bottom right. Link to the slides is provided in the Google Calendar entry. And after I started, I first had to understand the structure of the advisories. So that was basically the first step that I did, was to understand the data fields that we have. But not only their semantics, but also how are they related? Because this information is useful for me in order to understand what's the minimal set of fields that I have to provide, and the rest I could basically derive automatically. We have like data fields for identifier, which depending on the source can vary. For example, for NVD, this would be CVE, but for other data sources, the identifier can be different. We have a title that shortly describes the vulnerability, the description, which is a bit longer, the date that has been published, the affected range, which is a machine-readable version of the affected version range, the fixed versions, which is a list of concrete versions that where the vulnerability has been fixed, affected versions, which is human readable versions of affected range. So there's a correlation between these two fields, affected range and affected versions. Then the solution, which is an advice for the user, what he should do or she should do in order to fix vulnerability, credit, which is an optional field. URLs, some links, some useful links. The package slug, which is essentially like the package type and name concatenated, and the UID, but this one will be added in a later step. And there's some redundancies and interdependencies between these fields. So, for example, there's a redundancy between affected range and affected versions. If I know affected range, I can automatically generate affected versions. There's also a redundancy between package slug and identifier and the path to the actual advisory, because the path to the advisory in the advisory database is basically composed of package slug and the identifier. Then there's also an interdependency between the package slug and the affected range, because the affected range is expressed in terms of the syntax that's used for the package registry. For example, when you have the Maven package registry, you're using the style that's used for Maven packages to express version ranges. If you have like PyPy, there's a different style of expressing affected range. So this field here varies based on the package slug. And then we also have fixed versions, which shouldn't collide with affected range. So none of the versions that are fixed shouldn't fall into an affected range. And the solution should be correlated to the fixed version and the affected range. So the solution should tell the user that he should use one of the fixed versions. And there's then the transitive dependency between solution and affected range. So this information was kind of useful for me to understand what are the fields that I have to provide, and the rest I could generate automatically. So while I was working on this, I first started to write a sanitization script that used this interrelations and dependencies to automatically fix advisories by basically applying cross-verification. And this has the advantage that when we use like the same pattern for certain fields, we have a certain amount of consistency, which helps users. A good example for that is affected versions, for example. And when you're using the same template to generate the affected versions field, that's the same across all advisories, then there's no room for misunderstanding, basically. And as a side benefit, every component that I've developed for the sanitization tool could be reused for data generation too. And that's basically the first thing I would like to show in this demo, is the how you can sanitize present advisories or check the consistencies of present advisories in the database. And for that, can you see the terminal or?
Yep. We're stuck on the docs, the presentation.
Oh, okay. And I will just switch to. Now I'm on the terminal, I think.
Yep, correct.
Okay, perfect. Thank you. So this here is like the tool repository. It's the master branch, so there you can check it out, and it would like work exactly the same for you. And I've added the advisory database as a submodule. So this is advisory DB. The Gymnasium DB is added as a submodule, which makes it a bit easier for me to present and to try things out. And there's basically one single point to go to, which is a makefile. So I've created a makefile that contains or that documents and manages all the functionality of this tool. So this is basically the single point to go to where you can invoke all the functionality. And there's one make target called Sanitize, which is this one. And if you want to run a sanitization on your advisory database, you can run make sanitize, and it will run the consistency checks on the advisory database. And when I'm going now into the advisory Git status, you can see that a couple of changes have been applied to different YAML files. When I'm doing a diff between the master, we can maybe go to the first entry here. There is a change to Arabic prawn from the gem. And as you can see, there is an affected range which says greater than 0.0.0, but no fixed version. And the first version that we changed, it said that affected version 0.0.1, and solution, there's no solution for this vulnerability at the moment. So this here is like the text that's supposed to be read by a human, and the solution to. And the changes that the script applied were basically changed affected versions to all versions, which makes sense in this particular case. And it also changed the solution to, unfortunately, there is no solution available yet. The advantage of doing so is that this description is the same across all advisories. So if there's no solution, it will be just a single string, and the user can rely on that. And the second example that we have is wet cloth, which is also a gem. And here we have a fixed version, for example. And the solution string says that upgrade to version 4.3.0. And the affected versions also says that all versions before 4.3.0 are affected, which is also the same across all advisories. So the string that's being generated is sort of we're using some sort of template that's trying to avoid any confusions for the user. Okay, so.
Okay, this looks great. And do you have any example for more complex cases, like when the affected ranges is actually covering several distinct ranges? Like, you know, if you have several long-term branches like 1.x, 2.x, etc., etc.
Yeah, What I did is I basically represented this as a collection or a list of a scattered range, essentially. So a list of ranges, and the string will be generated for this list. So also, if you have like multiple entries, multiple version ranges, this will also work, because I'm considering this as a list of version ranges.
Okay, great, thanks.
Okay. So this was like the first part about the sanitization script, but now we come to the advisory generation part. So at the moment, or when we had our first meeting, we were talking about what data sources are most important, and I think NVD is the most important one at the moment, and we wanted to automate this advisory generation procedure for NVD first. And there are some challenges which are related to NVD as a data source. The first one is that NVD is very generic, which makes the entry selection a bit difficult, because not every NVD entry is related to a package. So it can be related to other software. But we are just interested in those entries which are related to those packages which we are caring about. So gems, PyPy, Maven, and so on. The related package name and type is not provided. The title is usually missing, so there is no title field for NVD entries. They use two different kinds of version representations. One is very specific, so it's more or less like a list of concrete versions. And the other one is a bit better for our use case because it's basically a version range we could directly translate. But you never know which one they're using, so you have to be able to cope with both version representations they're using. And the data feeds can be relatively large, between like 30, 40 megabytes when you're taking feed from a year. So as I mentioned in the last slide, this entry selection is kind of difficult because we don't know in advance if an entry is related to a package or not. And this is something we have to figure out. I had a conversation with Fabian, and he had this idea of using an information that's called CPE, Common Platform Enumerator, which is like a string that is associated with an NVD entry. So usually you find in an NVD entry a couple of CPEs that are linked, that are pointing basically to affected configurations. Like configurations meaning that you have like a vendor, a product, and a certain version ID. This is already very useful. You can consider this to be sort of a foreign key that you could use to link information to certain NVD entry. But it doesn't help us to get the package information because I mean the vendor, product, and version doesn't say anything about like a package type or name that may be related to the entry. And in order to get this information, what we can do is we can rely on data sources that we already have at our disposal. So we already have a GitLab advisory database, and in this advisory database we have CPE, so NVD entries basically, and we can determine which CPEs, common platform enumerators, are linked to this certain NVD entry. And based on that, we also can infer the relation between CPEs and package name and type. So this is basically how it works. So you have this GitLab advisory database. If you are looking at the CPE entries, like the NVD entries, which are present in this GitLab advisory database, then you basically ask the National Vulnerability Database, please give me the CPEs related to this CVE. And after you're getting this list of CPEs, you can link this together with the package information that's already present that you already can get from the GitLab advisory database. And based on that, we can generate a CPE map. And this is basically like a map between common platform enumerators and package types and names. So this is a bit reverse because we're using the advisory database to obtain this information, but it's already quite helpful because with this information, we can identify which NVD entry is related to a package, at least the packages that we already know. And for this process is called CPE Map Bootstrapping, and the supported sources for this procedure at the moment are the GitLab advisory database, brands of PHP, and RubySec, and I'm currently working on the CPE data feed because NVD also has an official data feed that we could leverage to get a package name and type information and link it to CPEs. And so I can also prepare a short demo for the bootstrapping procedure. So for that, I will just clone the repository, make a fresh clone because this takes a while. For the CPE bootstrapping, since we have like a couple of data sources which are used, and for every data source you have to basically make a couple of requests to the NVD website to get the CPE information. So it's I think for 3 data sources it takes like 12-13 minutes at the moment, so complete. I'm just like downloading I have included Friends of PHP and the Ruby advisory database as submodules. For that's also just to make things a bit easier. Okay, and I have also a make target for this, and this target is called Bootstrap, make Bootstrap CPE. And when I'm running this, this will basically go through all the submodules, like RubySec, friends of PHP, and our own advisory database. It will collect the corresponding CPEs from NVD and link them to package name and type. And as a result, we will get a mapping that looks like this, like a simple CSV file, so that you can also like add entries manually. And to pick one entry, so we have like here an example where you have the CPE string beginning, which gives you the vendor ID and product. And then we link this to a package type, which is PyPy in this case, and the name of the package is HPAC. And yeah, there's some additional information about including, excluding, but actually the first three columns are the most important ones: CPE, package type, and name. And yeah, this is basically the CPE bootstrapping procedure to obtain this this mapping, and we're using this mapping in NVD.
Sorry, Julian.
Yeah.
Your connection is dropping a bit. Could you repeat the explanation about this include string here?
Oh, yeah. So the idea is that that was basically one comment that Fabien gave in the epic, that we said that it would be nice to put X. So I've added an exclusion flag. So if you like some stuff to be excluded, you can set it to exclude, and it wouldn't be considered anymore. But at the moment, since this is like a sort of a ground truth. Every CPE that we have at the moment in this database is related to a package type and name. So at least the current state of this database, it wouldn't make sense to set like one of the entries to exclude. But I just added this functionality. Yeah.
Yeah, thanks.
So this was the CPE bootstrapping. And then we can move on to the next part, which is the advisory generation itself. So now we have generated our CPE map. We have the information about CPEs, package name and type. And when we're getting an NVD data feed, like a JSON file essentially, what we're doing first is we are running like a filter and split step. And what it does is it scans through the whole JSON file, and it tries to figure out if there's an entry that is relevant by looking at the CPE that's linked to this entry, and also looking at the package name and type that's linked to that. And for the relevant entries, we will basically write a single like JSON file. So we will write them into a separate directory as single JSON files. And we will also add some information. For example, by looking at this information here, I can already generate the package slug because I know what the package slug will be, and I can add it to the JSON file directly. I've implemented it in this way because it makes debugging a bit easier. If you have a separate file for every CVE, you can just go inside, and you have a small file where you can easily navigate through. So I'm writing them as single JSON file splitting. And then the next step is the advisory generation, which takes these JSON files as input and generates the actual YAML files with the file by using the package slug as a path and the CVE ID as the file name. We're also collecting the title information from CWE. So this is like the common weakness enumeration, which gives you like a short and sweet title for every vulnerability that you find. And the version information is also generated based on the information contained in the NVD entry. So the advisory generation is basically like a two-step process where we first cherry pick NVD entries, and then we generate advisories from that. And The generation covers all of the fields except for fixed versions, because this turns out to be a bit tricky, because for generating the fixed version field automatically, you have to get information from the package registries, essentially, which is due to the fact that the version bumps can be like different. So they're not always sequential. It might be that you have a version bump from 2.5 to 3.1.1. Never know. And so you cannot just infer them. You have to basically look at the package registry. What are the releases out there, and then you have to add them accordingly. The whole tool is implemented in a way that it's using streams. So we consider like the JSON feed as a stream. We never keep any state in memory, so that makes the process relatively quick to go through the JSON feeds. And also, the tool is implemented in a way that re-evaluation is always possible. And this is due to the fact that it might be that you're adding CPE map entries at a later point in time, and it might be even that you would like to re-evaluate a feed from 2017 or 2016. Maybe you find something new based on the CPE map entry that you just added. So, and therefore, I wanted the tool to be able to make re-evaluation possible in a quick way. So the advisory generation part can. So first of all, for the advisory generation, we have to get a JSON data feed from NVD, and we also have a make target from that. And this is called collect feed NVD. You can actually add the data feeds by adding basically an entry in this for this variable. It's like separated by spaces. And just so when you're going on the web page, on the NVD page, you find this table, and you see that they have like different feeds, and these feeds, they have like different names. So for this presentation, I'm using the CPE 2019 data feed, and
Julian, I'm still seeing the DB console now.
oh, wait. I'm sorry. Can you see my browser window now, or?
Yeah.
Oh, perfect. Thank you. This is like the table of JSON feeds for NVD, and they have different names. And for this presentation, I just used this CVE 2019 feed, but you could use any feed that's present in this. So this is like the CVE 2019 feed, and now I can just run make feed NVD, and it will like download the data feed locally. And it will also extract it. So when I'm now looking into this directory, I have the data feed. So this is like the NVD data feed. And has about a size of like 35 megabytes, around that. Okay, and after I've downloaded the data feed, the first step that we saw on the slides is this filter and split. So I have also a make target for that, which is called make filter and split NVD. And it goes through the data feed, and it only collects the one that are relevant based on the CPE map that we currently have. And it will generate different JSON files for them. And then we can find them in the NVD split directory. These are the JSON files that have been created by the tool. And this is like the, for example, one that is related to AIO XMPP. And also, as you can see here, we already added the package select because we already had this information, so we could just put it into the JSON file. Oh, and also you can see here that this is like the version syntax that's using version ranges from NVD, which is a bit easier for us to parse at least. This is now the filter and split step. And the next step after the filter and split step was this advisory generation step. So we also have a make target for this, which is called make generate advisories NVD. And this will now go through the JSON files, and it will write like the YAML files according to the format that we are using for the GitLab advisory database. It's also checking whether CPEs are already present in the advisory database, and if the date provided by NVD is newer than the commit date that we are using in the advisory database, it will change them, modify them. Yeah, the process is a bit slower than the filter and split step, because here we are actually communicating with CWE for getting the title. So we could make it quicker by maybe having some sort of local CWE database where you could get this information more quick. But at the moment, it's just sending requests to to the website, basically. And so now we have our advisories, which are in the advisories out directory. And let's just have a look at the first one. So this is, for example, generated for Bootstrap, and it contains the identifier, the title, which we took from CWE. It contains the description text, which is basically directly taken from the NVD description, the date, the affected range, and the range here is generated according to the syntax that's used for gems. So if this would be a Maven package, then the affected range field would look differently. And the affected version field here is generated from the affected range. So this is, for example, this is a case where we have a list of version ranges, basically, and this here is the text that we're generating from. So this is like the advisory generation part. Okay, so this was the advisory generation part, and now this is the whole approach, basically, in a nutshell. And there's one piece that's missing. That's the MR generation. We'll just show that step. But this is basically the whole overview of the approach, and I'm calling like step 2 to step 4. It's basically called NVD pipeline. And I've also created a make target that you don't have to invoke every single step, so that you can basically just run this make target, and it will run the whole pipeline for you. And the MR generation part. So now we only have generated the advisories, but what's still missing is generating or creating branches and adding one advisory to every branch, and then creating merge requests from them. So for that, I also have a target which is called prepare MR. And what it will do, it will basically create a branch for every single advisory that we have. So this is like the now the list of branches that we've created, and it's also adding the like using the description text or the commit message that's that's described in the contribution guidelines for Gymnasium DB. So it's generating MRs according to that. Let me just shortly go into one of these branches. So this is now an example for a yard, and yeah, it's the same as before, just the advisories. But I think, you know, in the initial meeting we kind of discussed about using either merge requests or issues, and I think that we agreed on using basically one merge request for every advisory. So this is basically the way how it's currently implemented. And this is like the generation part for that. Okay. So this was all about the DMR generation, and there's still a couple of to-dos. And one of the to-dos is to include the CPE dictionary into the CPE map generation, which would help us to get more mappings between CPEs, package names, and types, because the whole approach basically depends on that, on the CPE map. The better the CPE map, the better also the results of this approach. And we could also include heuristics to scan for interesting CPEs based on the description text of the NVDs. Then also one thing I'm currently working on is to infer sensible values for the fixed version fields, which is a bit more involved because you have to look into the package registries basically to get this information. Then in the epic, there's also mentioned that it would be nice to run this as a CI/CD pipeline to automatically generate merge requests. And yeah, then there's also one remaining item, which is using the GitLab API to automatically create MRs, because when I'm pushing the branches I have created, I still have to automatically find a way to automatically create merge requests based on that. And this is still missing. So yeah, so with that, I basically showed you the current state of the tool. I would be happy if you have like feedback or questions or.
Thanks a lot, Julian. Very interesting. Nice presentation. Thank you for the effort made into the tool itself and that presentation. Could you share your screen on the Google Doc, because I added some question there.
Oh yeah, sure.
And unless you have something else to tell us, I'm eager to ask questions.
Oh, can you see the doc?
Yeah.
Oh yeah. So regarding the CPE data feed, this is basically available on NVD. So they have like it's an XML file essentially. So they have a collection of CPEs, and with the CPEs, they also provide links to resources, and these resources can be also links to package registries. So you could use these links in order to identify if a CPE is related to a package, and this is kind of useful for us too, because we could generate better CPE maps from that.
Yeah, that's very interesting indeed. Do you have a rough idea about how many CPE are in there, or what the coverage?
Oh, it's a huge file. I forgot the exact number, but I think a couple of 100,000. It's quite large, so it's a very useful resource.
Sorry, I didn't hear you. Like, the connection was dropping.
Oh, sorry. Yeah, I mean, I forgot the exact number of entries that we have, but it's a fairly large file. I think I should have it in my short check.
Yeah, so it might be indeed very interesting to leverage that to improve our mapping. Because this was the next question I had. Currently, if I get it right, if we don't find an entry for this CPE in our map, we just skip the CV, right?
Yeah, that's true. So there's still some manual work. So when I'm preparing the first merge request, I still will check for the NVD data feeds for certain. Maybe I will use a regular expression or something to check if there are like certain NVDs that still might be interesting, and will add the corresponding CPEs manually. But they only have to be added once, and if they're there, they will be considered in the future. But it's true, yeah. The CPE map is basically at the moment the single ground truth used for cherry picking.
Okay, because then we have a risk to miss new CVs that can be relevant for us. So we should think about, I mean, I just like the fact that we still need to have a manual check, but I don't see a way to avoid that right now to make sure we're not missing a CV.
Yeah, I was thinking that maybe I could incorporate a functionality into the tool that helps you to scan for interesting CPEs by using maybe a couple of patterns or regular expressions that we could adjust. So we're getting better and better over time, and then use this to kind of audit an NVD feed for CPEs that we missed that are not present in the CPE map, but that would be maybe still interesting to add. I mean, this would be fairly easy to implement. Of course, then we also have the regular expressions should be at least general enough that we don't run into the problem of missing something that may be relevant. But yeah, that's a good point actually.
I just have an idea about this. Maybe we can have another like blacklist of CPE, so we can just like found relevant CPE we can add for like manual creating advisories, and the rest which not is blacklisted we can just send like for manual manual curation, and then we can improve both CPE and CPE blacklist.
Yeah, makes sense. That's also a good idea too.
So on each run, the tool could create like an issue listing all the CV that we skipped because it was not matching a relevant CPE. And based on that list, we should create a blacklist file to put the CPE that we think are not relevant to us, so that any on the next run, if there is a similar CPE, we just ignore them and don't put them in the curation issue. Makes sense. This is what you were telling Tatiana, right?
Yeah, so it's basically like what I'm doing. So like when I have to manually check NVD, that I know that, for example, Jira or some other known tools, they like have a lot of found vulnerabilities. So I just keep them when
so you could just dump that brain memory into a JSON file for us?
I wish I would. So basically, I like train my like neural network to find such CPE, so we can do it automatically.
Yeah, adding this then to the doc, and Juliana, I will leave that to you to add it to an issue for next steps. And because I think this is mandatory before switching to this new tooling, because missing a CV is definitely something we don't want to do.
Yeah, that makes sense. You know, what I was saying in the earlier slide was this capability of reprocessing. So I was thinking that if you can quickly reprocess NVDs, then missing one is actually not that big of a problem, because when you just, you have to, once you've noticed that you've missed one, you could basically add a CPE entry to the map and then rerun the whole analysis essentially. So at least this process would go relatively quick, but it's true. I mean, it's better if you could get as many NVD and relevant NVD entries in the first go as possible.
I agree, and I like this because this is also super useful when we will add support for example, a new package type. So we can quickly reprocess the whole DB and get a lot more information for all CVEs. But again, I think we had a discussion recently with someone, I don't remember who, but it's good to correct a mistake. Like we missed a CVE and we can quickly respond as soon as we know we missed it. But the problem is that we can maybe stay for several weeks without knowing about we're missing the CVE, and then we have a customer reporting that, hey, you're not checking against that CVE. Why? Oops, we just missed it. Sorry. We can add it quickly, but we already harmed the users because we passed several weeks without checking for it. So
that's a valid point.
Okay. If there is no more comment on this one, switching to the next question, which was about fetching info from CWE. Isn't there any risk of rate limiting here?
Yeah, that's actually a good point. So I think we have to scrape basically the whole CPE. I mean, we could basically just mirror it locally and then get information from there, because querying it takes quite some time, and this makes the whole process unnecessarily slow.
Right. And the last one I got was about this merge request creation. I don't know if you're aware of that, but you can use push options to automatically create a merge request when you're pushing a branch. So you can create a branch locally and call git push with some options to automatically create a merge request.
Oh, cool. Then I will use that. I thought that I have to maybe use the GitLab API for that, but I will look into that. That's great. Yeah.
I'll try to find the documentation. This.
Okay, great. Thank you very much. Yeah, so I will create issues for the CPE discussion we just had. Yeah, blacklisting is actually a good idea. At first I was thinking to use regular expressions, but there's also the risk of missing something. Maybe you could use both. Yeah.
And man, this is maybe getting too deep and we're already 15 minutes. But I was just thinking about maybe instead of creating an issue, we could create directly a merge request with adding all those information to the blacklist, and then manually curating that and removing the entries that are relevant after we did this manual check, so that we speed up a bit this process. But anyway, that's implementation detail. Because that in the issue then. Right. Thank you very much again, Julian. That was very, very interesting topic, and you did a great job. on all those process and workflows and tooling. Thanks again.
Thank you very much. And
yeah, thanks. That's awesome.
Yeah. I really appreciate this.
Yeah, we can hear the voice from people manually curating and feeding the database today. All right. Any other question? Wow.
Can you give me CVSS data? Get that into the. Please, please, please. No, I'm just kidding. No, this is awesome. Thank you, Julian. It's well put together.
Actually, is
it possible for us to use this somehow now?
Yeah, you can. So everything I showed was based on the master branch, the current master of the tool. So you could run it instantaneously. The only thing you have to do at the beginning is you have to, after pulling the repo, you have to run a make update, which will pull all the submodules, and after that you can invoke all the targets which are there. And yeah.
Okay. Thank you.
Regarding the recording, where should I put it? Is there some place where I could upload it?
You can stop it now.
Oh, yeah.
So that we don't have all this discussion within the recording itself. But you can just upload that to YouTube.